All right, we're going to get started. Sounds like this is broadcasting into the room. And good morning, everybody. Welcome to the hangover slot of Identiverse 2023. My name is Justin Richer, and I am here today to talk about standards. My background is in computer science, which means I have degrees in telling computers what to do. And this has been a large part of my job for a long time here. And it's really important that we have people to tell computers what to do, because computers are insanely dumb things. They do only exactly what you tell them to. They won't do anything else. They won't do anything that you didn't tell them to do. And they do it exactly as they were told. The problem, of course, comes from the gap between what you think you told the computer to do and what you actually told the computer to do, right? All good software is just bad software that is currently behaving well, right? And we haven't figured out what parts are actually broken, what parts are actually hidden in there. Somewhere in my career, I discovered this entire world of technical standards. This was quite a while ago, and speaking of quite a while ago, if you can hear these slide transitions as I'm clicking through them, how's your back feeling today? So I discovered the world of technical standards, and this is a really important space. Standards allow us to plug things together. We agree to do things the same way. Your stuff works with my stuff, and everything's happy. This is great. We've got all sorts of things that rely on standards, and in fact, I talked about this a few years ago at the predecessor to this conference, the Cloud Identity Summit back in 2016. It was a Lego-filled presentation called So You Want to Run a Standards Group. It's up on YouTube, and one of the key takeaway points here is that standards are in fact made by people. Right? Standards are not invented by computers for computers. They're made by people for other people to actually go and build stuff. And come on, do the thing. There we go. The entire process of making a standard boils down to a couple of simple steps. You find a problem, write down a solution, and get everybody to agree to the solution. Seems pretty easy, and it's in fact not all that easy. But especially that last step, getting everybody to agree. But this seemed to be a really compelling thing. When I learned how the sausage was made in all of these standard systems, I was like, you know what? I want to be a part of that process. This is a really compelling thing. Find a story that you're really interested in, that you're passionate about, and go tell that story and find a solution to that and tell people about that solution and figure out how to solve these things. And then, of course, other people are going to solve it the same way that you did, because that makes a lot of sense, and then everything's going to work together, as long as you all write it down, and it's going to be fine at the end of the day, right? But the thing that kind of held me back a little bit, especially at the beginning, was that this is documentation. My degree's in computer science. It's not in documentation. I didn't like the writing down things for people to read part. It was not compelling to me. This was not interesting to me. But one day, I had a bit of a realization about this work that was happening out there. I realized that, in fact, I was still programming. Writing a standard is a lot like writing a program. It's a lot like writing software. The programming here, the programming language that we have, the input to this process is the specification text. The output of the process is a functioning, compliant implementation of that standard. Like, you are writing something so that you get that output. That is the entire goal of the process. And once I started to approach the standardization process as a programming and engineering exercise, it made a lot more sense to me. We've even got a programming language. These things called normative terms. They look a little bit different in different standards orgs, but they fall into three major categories here. And I'm being very careful about what I say in this next part, because Heather Flanagan is in the front row. The first category is the requirements. These are the things that you have to do. You don't have a choice. The standard says you must do this or must not do this. You don't really get wiggle room around that. It says you do this, and so you do it. Then backing that off a little bit, because the world is not all completely deterministic, these are things that are really good ideas. But if you don't do them, you should really understand why you're not doing them. That's the intention behind a should or a recommendation in these specs. But also importantly, if somebody else that you're working with doesn't do what's in that should, you're not really allowed to get mad at that, because they're allowed to have their own really good reason, presumably, for not doing the thing that it says that they should do. And you have to be okay with that. You have to be able to deal with that in your system. And then finally, the wiggliest of the bunch is the may. These are the options in the systems. This is where something is explicitly allowed to happen or not happen. Which means that if something is listed like this, then you can't get mad if somebody does it or doesn't do it or anything happens, but you need to be prepared for something like that to happen, right? That's really the value of this thing, is preparing you and preparing your implementation to be able to handle all of these different options that people may or may not do. So bring these all together, and we've got a pretty decent programming manual, along with all of the examples and sort of the explanatory prose around this programming language. We've got a pretty decent programming system, and this leads us to our goal of interoperability. Interoperability is the ultimate goal of standardization, because really interoperability is just a successful connection without pre-planning everything. I can read one side of the standard, you can read the same standard, and we plug things together, and they work. That is the goal of interoperability, right? And the good outcome is that everybody follows all of those musts, and different systems are implemented in different ways, but in ultimately compatible ways, and everything works right out of the box. That seems great, right? Yeah, no, that is not at all what happens in the real world. I think we all know that. Part of that is due to the, just sometimes there were just mistakes in programs, the whole good, bad software thing. But really what ends up happening is that people take a look at a standard, read it and interpret it, and build it in the way that they think makes the most sense. And that's probably not going to be the way that the standard's authors intended for it to be, especially right out of the start. This surprised me a lot when I got into the standardization space, that there could be so much variability. But then I realized that I had focused a lot on how the sausage was made, and I wasn't paying any attention onto what was done with the sausage. Right? The standard is not the end point. The standard is one step in the process. It's not enough to just write a program, you have to run it. You have to execute that out into the space and see what the results are, to see what's going on. So I still contend that writing a standard is a lot like writing a program. There's a lot of similarities. But you're writing it for the absolute worst possible runtime environment that has ever been devised: human engineers. Standard text has to execute in the brain of an implementing engineer, and it's not going to go the way that you expect it. So imagine writing a piece of software where anything that you don't explicitly call out is done differently, but only sometimes, not all the time. So for example, when working on the HTTP signature specification, we had 3 different implementations, all implemented this one piece of the signature spec, and they all came back doing exactly the same thing. The bits were all packed in the same way, and everything was great. A 4th implementation rolled up and wasn't compatible. Our first thought was like, oh, well, they had a bug, or they misread the standard, and we all kind of compared notes, and no, they had implemented it exactly how the standard said to, but differently, somehow. And so we had to figure out how to make the standard more specific. It was a matter of like byte packing and ordering things like that. It was a really simple thing to fix. We just had to agree that this is something we need to be more specific about for everybody to actually start work together. You also have cases that we'll talk about in a bit where explicit instructions might get ignored sometimes. Even the things that you say must doesn't mean people are always going to do that. And the most important bit here is that all of the assumptions that you made are not universal. The things that you think going into a system are always going to work the same way are not. The HTTP signature example, that little bit that I was talking about was the output of an underlying crypto library. On 3 different platforms, the bits came out in one order, and on one other platform, it came out in a different order because it wasn't specified. Once we specified it, it was no problem. The reason that this happens is that people are just going to take the text that's there, make their best interpretation of it, and try to make it work, right? It's a messy, messy process. So let's take a programming example. I'm going to give you a specification. We're going to write the Hello World program. Anybody that's done software engineering before is familiar with this. It's a really common sort of first program to write in anything, in many, many platforms. So this is what it looks like in Python. We print out Hello World. All right, we moved to basic, and again, if you can hear these slides, you can probably read this code. We print out Hello World, and then of course we end the program because otherwise the interpreter hangs, because that's helpful. And in Java, we need to grab a lot more syntax in order to do something this simple, but somehow it's enterprise grade, I guess. And then Rust, we make a main function to print this stuff out. This is all pretty straightforward. These are all implementations of Hello World. They should all be compatible, right? Well, let's take a look at the output of all of those programs. I gave the specification, I want a program that prints out Hello World. This is what each of those 4 programs printed out. So yeah, they printed out Hello World. It's not exactly the same, is it? Right? It gets the intent, but not quite the specificity. So now we're going to run this program on an even more unreliable platform, the Italians. Now, Vittorio was supposed to be here in the audience for this, so we have David helping out here. So please, if you could, can you say, hello world? No, hello world. Buongiorno mondo. No, that's not. So he did exactly what I asked in the context that made sense to him. Buongiorno mondo is hello world. Like he fulfilled the requirement in completely the way that that doesn't help me, right? This is the kind of thing you have to work with when you're dealing with engineers implementing things. Now, for another example, I taught a class to fourth graders a bunch of years ago, an intro to computer science class. One of the exercises that we did early on was I would get up front of the room and the kids would program me, a rather petulant robot, to draw a smiley face on the whiteboard. And inevitably, after a little bit of fumbling around at the first bit, somebody would say, okay, you know what? Draw a circle, make two eyes, and draw a mouth. And I would do that. Because that's how you make a smiley face. You draw a circle, you make two eyes, and you make a mouth. And someone would say, like, that's not even a mouth. What are you talking about? And it's like, sure it is. I just didn't draw the rest of the dog, cat, animal thing, right? I made a circle, two eyes, and a mouth. It's a smiley face. So after a bit of consternation, the kids would be like, okay, we need to be a little bit more careful here. We're going to draw a big circle. Make sure there's a lot of room for everything. So they get more specific about that. And like, okay, that worked great. We're going to put a dot in the circle for the eye. No. We're going to put two dots in the circle and space them up and put them up here. Okay, we're doing good. At this point, inevitably, somebody gets really excited that we're almost done. There's one more bit. Now make a line in the bottom of the circle to make the mouth. No, I meant inside the circle. No, I meant make it curved. No, I meant draw a line with it curves up and it doesn't touch the edges of the sides. So the kids would understand how specific you really need to be for that interpretation to go the way that you intend it to be. Because deterministic compliance is not an easy task. Both of these are the result of draw a circle, draw two eyes, and draw a mouth. And they are completely different and incompatible interpretations of that. This is the world, this is the execution environment that the standards we write and the standards we use has to execute in. Imagine an even more complex process of getting somebody to make a sandwich. There are some hilarious videos of people doing this to their kids online. I'll leave that to you. But I've long thought that the true genius of the Star Trek food replicator is not the molecular level matter manipulation. That's cool and all. But the fact that you could walk up to it and say, tea, Earl Grey, hot, and not get a bag of churros is just, that is the phenomenal piece here. The fact that it was an intent-based interface and it worked, that's the true fiction in this science fiction. So standards have to deal with this problem both as we run them and as we write them and as we execute them. But we have to keep in mind that the people writing these standards are the same platform, right? It's implementing engineers that are coming in and writing down these standards. And that means that there's a lot of motivations that goes into these things. Now, some of that, some of the outfall of that is just that, you know, good standards are kind of a subset of bad standards that we haven't figured out where the edges are yet. Right, but it's also the fact that a lot of times people will write something and it seems like it's good enough, so don't touch it. Don't mess with it. Like that HTTP crypto bit, we could have just told the other person, like, no, fix your implementation so it matches this. And that happens a lot in the outside world. Because at the end of the day, engineers, we need to get things done. We need to finish off our specs, we need to finish off our systems, we need to build systems that actually work. So interoperability is great and all, but shipping a product is a lot better than that. If I can somehow, though, manage to do both, and if I can even make it so that I am standards compliant, I can claim compliance with a standard, and yet do something that's a little bit extra sparkly, that's market advantage. Like, a lot of people are trying to do this. So let me tell you the tale of TCP. So back in the day, Microsoft had the dominant browser platform. But we'll get back to them in a sec. I forgot about this slide. The way that TCP works in the standard is that it is a bidirectional communication setup, right? You do a synchronization, you get an acknowledgement, you do that in both directions, and only after you do that, you start sending data. So like I mentioned, Microsoft had the dominant browser platform in Internet Explorer. They also had a web server product. IIS. So somebody at Microsoft figured out that if IE is talking to IIS, we can skip all of that TCP handshake nonsense and just start chucking data across the wire. And IIS was prepared for that. So you don't even set up a TCP connection, you just make the connection and start going, and without even doing the handshake, IIS will respond to that. This works. Microsoft controlled both sides of the tunnel. They could do that. What this meant, though, was that IE, when connecting to a non-IIS platform, the server following the standard for TCP handshake would be like, what are you doing sending me data? No, start a TCP handshake now. At which point IE would go through a code path that was basically, fine, and it would start a proper TCP handshake, and then eventually the data would flow. Same or similar thing happened with TCP teardown. You're supposed to have a bidirectional teardown, IE to IIS, only did it one way. Because they controlled both sides of the stack, they could detect the situation, and so it worked all right. The result of this is that connecting IE to IIS was really, really slick, and IE to anything else was slower. And since IE was the dominant browser platform at the time, this meant that it meant everybody else's web servers were slower, according to Microsoft. The reason that everybody was slower was that they were following the rules and Microsoft wasn't. So even though IE was blazingly fast, it really didn't work out all that well in the end. So what do we do about all of this? The first thing that we need to care about is precision. Precision of our language, precision of our systems. If you're building a specification, make it specific. It's right there in the word. I am amazed at how many specifications don't do this piece. And when you're writing this, assume that anything that you don't say is going to be different, and different in ways that you don't expect. Right? Spell out things that you don't think you need to spell out. Never assume that your assumptions are going to be shared by other people. When you do have but it's not enough to just have normative requirements. Your normative requirements need to make sense to the implementers. I don't know how to follow that street sign. I don't know what to do there, but I have to do it. So what that means is that me as an implementer, I'm going to ignore a street sign that I don't understand because I'm probably going to come up with something else. And you got to watch out for phrases like this. I kid you not, I copied and pasted this from a real specification, a real standards body published specification where something may require, allow, or prohibit use of something else. This gives me absolutely no information that's actionable. This doesn't tell me anything about what to expect. Right? This is not useful. So the next thing we need to do is be aware of the scope of our system. Scoping is deeply important. We talked about interoperability as the goal of standards, but interoperability of what? What do I expect to connect to each other? It's not going to be everything all the time. Standards layer on top of each other. So we need to be clear about what those expectations are. We need to keep focused on what the interoperable parts are and how they work, and make clear lines for where we extend things. Now, scope is absolutely essential to building a good standard, because if you allow the scope to grow too large, then you're going to specify everything end to end, and there's no layering, there's no flexibility, and it's just like this monolith is going to trudge along and eventually get replaced or ignored or just fall over under its own weight. Thank you, WS Star. And we need clear boundaries to know what's in scope and what's not in scope. But importantly, that last bullet is the most important here. Other people can do whatever they want outside your scope, and you need to be okay with that. So, for example, we're going to define a standard for a house. Seems like a good house. It's got a roof. It's got some upstairs windows and stuff like that. We're going to leave this part of the house out of scope. You know, the front door, right? That's what we're going to put here. We're going to put a front door here. But we want that to be where the innovation is. We want that to be where, you know, the magic really happens. So maybe I want some side lights. Maybe I want some, you know, garden planters out front there. Maybe I want some, you know, large French doors or a little portico. I want to be able to have a lot of flexibility. It's out there. So I'm going to make a really big space in my standard definition of a house to make sure I can do lots of different things. But when you leave a train-size hole, somebody drives a train through it. And you can't be mad about that. You need to know what the shape and extent of the spaces you leave in your specs are, And when you're implementing them, you need to be aware of what those spaces are too, because the other people that you're trying to implement with are going to do things like this. The assumptions that you make about this being a space for a front door, it doesn't apply. It's a hole in the front of the house, and if you can drive a train through it, somebody is going to drive a train through it. So the next big thing that we can do is test. Do actual hands-on testing. Take two implementations and plug them together. Like I said with the HTTP signature stuff, that's what we did. We had a handful of small implementers early on in the process, and we tried our stuff against each other and see what worked and what didn't work. If you can plug in everything to everything else, right? This full matrix testing is a really lofty goal. In practice, it's really, really, really hard to pull off. So wherever possible, use automated testing. Make a test harness that defines the boundaries of the interoperability of the system. Give me a way to plug in an implementation, and that can be a limited way to plug in an implementation, but give me a way to plug in an implementation so that I can see through automated, predefined tests what works and what doesn't in what I built, right? A really fantastic example of this is the OpenID Foundation's Conformance Suite for OAuth 2 and OpenID. There were some talks about it here earlier this week. This is a really great test harness because you can show up with your implementation. It will run an entire battery of tests for you and tell you what it did, how it, when it passed, how it failed, and give you back all of that feedback. And this is a fantastic resource. We need more test harnesses like this across all of our different systems. These are hard to build, even harder to maintain. There's a huge investment in this. Absolutely agree, but they are incredibly valuable. Wherever possible, obviously, do both. Do both plugging things in and automated testing. Do as much as you can. And finally, the important thing that we need to do is be realistic about our systems, right? In our standards, there's some really common traps that people fall into. We leave those train-size holes, assuming that everybody is going to put a front door there and nobody's going to drive a train through it. Watch out for those, right? We deliberately see things that are not defined because it would break somebody's assumption that they made. This happened with the PXE standard because Google had a plain text PXE, so that's now encoded, even though it is also now standardized as don't do that from a different spec, right? Sometimes what looks great on paper you can't actually do. That's why it's important to build and test and plug together. And also be aware of the fact that a lot of times people are reading the text. They may have it right, they may not have it right, but they thought they do. Like a lot of times people doing these implementations, like you got to assume most of the time people want to get it to work, right? They're not trying to deliberately break things most of the time. And so they think that they're doing the right thing. And that can be a problem. But good standards and good execution of those standards does lead to good interoperability. Those precise directions, the well-defined requirements, and adherence to those requirements covered by testing allows things to often, not always, but often work together. When you're doing your implementation, take the normative stuff seriously. That must really does mean must. But when you decide not to follow a should or to follow a may or something like that, document that. Figure out where the scope boundaries are, what they're shaped like, and ultimately always be prepared that somebody else is going to make a different decision from what you made. At the end of the day, know that standards only document a solution. They don't really give you the entire story of how we got there. They can give a lot of information to that in the pros, but you're not going to get the entire backstory. You're going to get one solution to a problem space. Which means that the assumptions that go into this vary, and somebody else is going to make different assumptions and may or may not really need to follow that. Because compliance in this space, in this technology space, it's largely self-regulated. Like Microsoft with the TCP thing, IETF likes to say there is no protocol police. Nobody's going to come kick down your data center because you're not following TCP. It is, however, socially enforced. Microsoft did eventually fix their TCP stack so it stopped behaving badly. Google, at the early days of OpenID Connect, had some weird behavior about their OpenID Connect implementation that they were like, it's already deployed and we're not going to change that. Then the Conformance Suite came out and everybody could see exactly how Google was broken. That got Google's attention enough to actually fix their implementation. So this social pressure can and does work, right? But this interoperability only matters if people care about it. So it's up to us as implementers and as standards authors and as people working in this community to make sure that they do care about it. That social pressure that allowed Microsoft as the dominant browser vendor to go off into the woods is the same kind of social pressure that made them actually fix things. So in the end, please, be a good runtime environment. Thank you. And I think we have a couple minutes for questions. Yes, I'll repeat it on mic.
Yeah, one of the things I think is interesting in spec work that I've done is you can have, like it's supposed to be this kind of holistic, like everyone is buying into the desired solution, and then for that solution, you can have outsized influence from implementers. And how you tackle that as a working group is a fascinating thing to have to learn how to do. Do you have any guidance on that?
So the question is about, in the standards development process, there is outsized influence from implementers, and I'm assuming you mean sometimes particular, especially large implementers pushing standards in particular ways, right? Honestly, some of the best ways to combat that are to get more voices in the room. It's not always easy to do, but diversity in this space is something that is a struggle to build. But it's really, really important. Because if you have people that show up and it's like the same 5 people from the same 2 companies always saying the same thing, that's not really consensus, that's a cabal. And the best way to combat that is good governance and organization inside a standards body, which can make it robust against things like that. But even that will only work if there are other voices in the room that can actually do counterpoints. So a particular example is a few years ago, I was chair of a working group in the IETF, and we were looking at whether or not to take on one particular piece of work. And my co-chair and I, we put out the call, like, is this actually, is this something that the group wants to do? And there were like a dozen messages saying like, yes, this is a great idea. Most of them from people who had never shown up at any meetings or joined any conversations before. After a little bit of investigation, we realized that it was all coming from basically 2 companies who had sent their representatives who had gone around to other people and say, hey, I need you to thumbs up this so that it looks really good. At the end of the day, the call that we were able to make with that was that there was not wide enough support in the group to do that. Because there were people that had very real reasons, like, no, we probably shouldn't be doing it this way. But if we were working on just a pure voting open system without understanding what was going on into that, then it would have gone a very different direction. And I stand by that decision to this day. Great question, though. If you want more about sort of how that whole space works, I do encourage you guys to look up my talk from 2016 at CIS. It is on YouTube, and it was another fun talk. So. Anything else? All right, thank you all very much, and enjoy.